Hello everyone, today we're going to talk about sampling with Honeycomb's trace-aware sampling proxy Refinery and how to get the best sampling out of that we can. My name is Davin Taddeo. I am a customer architect with Honeycomb and have been here for about a year and have been working with customers in implementing Refinery and tuning it, and am hoping to pass on some of that info to you. We're going to talk a little bit about sampling theory, and then the different types of sampling that Refinery can do, followed by how Refinery uses data from your traces, your distributed traces, in order to implement rules and the various different samplers that we have in order to get the best effect for sampling. Starting out with a little bit of sampling theory, when we talk about sort of data and data analysis of any kind, with any sort of product like Honeycomb, you're dealing with wanting to have all of the data. You want every metric, every trace, every log. All of that provides value, and when you do analysis on that data, you know that it is accurate. You're able to view things with, your perspective and scope of view have high fidelity and precision, but it's also expensive. So that's where we sort of introduce sampling into the mix, and this is true for most data analysis. Is that just it gets expensive to have every bit of data. So we take some of it and use that to extrapolate data in order to save costs. But this does cause issue. It does cause a loss of that accuracy. But we can measure that loss of accuracy. We can measure that via standard deviation and margin of error that is generated from that, basically sort of giving us an analysis of how far we are from the mean of data that we've sampled. We can tell sort of how accurate our picture is that we've devised after sampling the data and after accounting for having sampled the data. We have an equation that we recommend for looking at that data and seeing what that margin of error might be. This is an equation taken from a presentation given by Heinrich Hartmann at SRECon in EMEA last year. Basically, what we're doing here is we're seeing that we have our original data, our original traces or values, but we're reducing the fidelity, we're reducing the accuracy by sampling. So we're only getting a percentage of the original values. And then sort of on the other side of that, when we go to portray that data, we multiply that again by the amount that we sampled in order to get a rough idea of our sampled, of what the original values might have been. We calculate the standard deviation, the equations there on the bottom, and I'm gonna go ahead and run through a couple of examples just to give an idea of how this plays out. If we look at this, we're gonna start with just 100 values. And we're going to do 10% sampling, so we're going to keep 1 in every 10. And basically for 100 traces, we're going to keep 10 traces, roughly. And then we're going to multiply that or divide by 10%, multiply it by 10 again. And on the end, we're going to have, 100 values. But those values are going to be, those 100 values are really represented by 10 real bits of data, real traces. If we run this through our equation, we're actually seeing a pretty high margin of error, 30%. And that's really not sustainable. So, 10% doesn't seem like a lot of sampling, but in this case it seems like it's really just killed our accuracy. That said, when we do the same volume of sampling but on a higher set of original data, our margin of error goes down. So if we run this through again but with 1,000 values, or 1,000 traces in our original data, we come out with roughly 100 real values. Multiply that again, get 1,000 sampled values, but our margin of error this time is only 9%. And for something relatively benign or information that we don't need to be super accurate, 9% is not that bad. And you can extrapolate this further. If we do 10,000 values, 1,000,000 values, we reduce that margin of error. So we can do that calculation and sort of see what's acceptable. So when we start looking at sampling, the thing we want to remember and what we're trying to determine is what is an acceptable margin of error, what's an acceptable standard deviation for the data that I'm sending. So Refinery helps with that process in a couple different ways. So when we talk about sampling with a lot of products, we look at basically what we call head-based sampling, where in our instrumentation we say we're going to have a sample rate of 1% or 10% or whatever, and it's going to say every time you start a new trace, it's going to say, should I start a trace or not start a trace based on that sample rate. If it doesn't start a trace, you don't get any of that data. It has no idea whether, that event that would have been traced would be an error, would be useful data, anything like that. It's very efficient. Within Refinery, we have a sampler, the Deterministic Sampler, which I'll get into later, which also, again, doesn't look at any of the data underneath. It just looks at the trace ID and says, throws that through a hashing equation and says, I keep it or I drop it. And that's how it samples. So that's sort of what we talk about when we talk about head-based sampling. Refinery, we do tail-based sampling or trace-aware sampling, where we're able to actually look at the data of the span attribute values in your trace and make decisions in our sampling based on those values. So it's very much a sort of informed sampling process with the goal to be able to reduce the margin of error where it is most necessary in your business. So in your need for accuracy, you want the lowest margin of error possible. So moving into that, we're going to talk about the samplers that Refinery uses and can use. The first one, I mentioned this briefly, the Deterministic Sampler uses a hashing algorithm against the trace identifier field, usually trace.traceID, and it makes the sampling decision based on that. We configure it with a basic sample rate setting. This is a 1 in X, not a percentage rate. So if you set your sample rate to 10, it means one trace in every 10 will be kept. If you set it to 1,000, one trace in every 1,000 will be kept. It's a very efficient sampler. It takes pretty minimal computing RAM resources compared to DynamicSampler or Throughput-Sampler or other samplers. And it's really good for consistent higher volumes of traces. So basically, you want to apply this to data where you're fairly certain of how many traces per second you're getting, and so that you can calculate your margin of error and be happy with what that margin of error is. So you want that, you want consistency in order to use this sampler. We also use it within our rules-based sampler, which I'll talk about later, to not sample specific data. So you can actually set the sample rate to 1, in which case it keeps every 1 out of 1 trace, and it doesn't drop anything. Getting into a little bit more magic that Refinery does, we have dynamic sampling. The goal of the dynamic samplers is basically to weight rare and frequent traffic differently, so that we can end up with targeted sample rates that still maintain sort of an accurate standard deviation, even when traffic is varying or sporadic or something like that, so that you still get, high fidelity on the rarer traffic that is going to be more interesting when you're analyzing things. So thinking about this, think about your HTTP status codes. You get a lot of 200s, some 400s, and hopefully very few 500s, but you want to make sure you get all the 500s if you can, because those are usually pretty important when you're trying to debug problems that customers are facing. So the way that the dynamic samplers do this is basically they create a key base filled with keys based on the data contents of your traces. So it looks at all the spans in your traces. You generate a field list of specific span attributes that you care about, and then it looks at those attributes across all the spans in a trace, and it generates a key out of those values. And once it's generated that key, it will, for every trace that comes through with the same key, it creates a count for that key. And then based on the count of a key over a specific period of time, usually like a second or 10 seconds, it will generate a weighting for that key, so that when new traces come in, it can say, oh, I have this weight, I should be sampled or not according to that. So to give you an idea of how the dynamic sampler builds these keys is, if we look at our trace here, we have trace A, we have 2 spans in it. We have a field list for status code and method. Both of our spans have 200 status codes and get methods. So our key is going to be 200, get. But what happens when our spans aren't the same? With a secondary span or trace here, we have the first span 200 get, but the second span has a 500 status code and a get. So this actually we combine it because it's the accumulated values for those fields in your entire trace. So we have a span with a 200 status code and a span with a 500 status code, so that becomes 200, 500 with the get method in our key. So those are the 2 different keys we've seen between these 2 different traces. So then the dynamic sampler looks at how frequently those keys have been appearing, and when each trace comes in, it applies a sample rate based on the weighting, which is based on how often we see each of those keys. So hopefully traces with 500s or 400s are likely to be sampled with more maximally, meaning we're keeping more of the data than those with, say, a 200 status code where we're getting a lot of them. And we're trying to basically come up with a target sample rate that we want sort of all of this to work out to. So we have, 200s might be sampled with a sample rate of 7, and 400s might be sampled with a sample rate of 3, and 500s are sampled with a sample rate of 1, and ultimately we have a sample rate of 4.5 for all of our traffic that's going through this dynamic sampler. So the sampler that we prefer to use, we have 2. We have a dynamic sampler and the EMADynamicSampler. We recommend using the EMADynamicSampler. This is the exponential moving average dynamic sampler, which basically is regularly computing and looking at the counts for our different keybase to see if we need to adjust the weighting for different keys. This is useful if your traffic is a little bit more volatile. The EMADynamicSampler is going to react a little bit more quickly and change sample rates for the different keys based on the changes of traffic. It's going to work out a little bit better. Some of the gotchas of using the dynamic samplers. Remember that, so weighting the dynamic samplers is based on the volume of traces in each key. So sampling a key with very low volume will be maximal. There's more real data is going to be kept because Refinery is trying to ensure that we have accurate data when it gets to Honeycomb. And if you were to sample those, the low volume of traces, if you were sampled those with a high sample rate, you would find that you were not having very accurate data on the other end when you went to analyze things in Honeycomb. So when you're building your field list and you're providing it to the dynamic sampler, you want to make sure you don't have too many keys. If you have too many keys, you're unlikely to get enough volume on any given key to be able to sample them with any real reduction in events coming through to Honeycomb. And you're likely not to match your goal sample rate. Also to note, an individual refinery instance only sees the traffic that goes through that individual refinery instance. So the weighting of the dynamic sampler on the different keys is based solely on the number of that particular key, of those keys seen on that specific node. It's not aware of what the other nodes are seeing or doing. So you got to keep that in mind as you think about clustering. The more nodes you have, the more traffic volume you really need to send through your dynamic samplers. All right. Finally, we have the total throughput sampler. Throughput-based sampling attempts to meet basically a goal throughput rate of a fixed number of traces per second per refinery node. This is a really useful strategy if you need to, quickly get volume usage under control, or if you have fairly uniform and consistent volume of events that you feel comfortable narrowing, limiting to a specific throughput. Similarly to the dynamic sampler, this suffers from a high key space where you have too many keys. We recommend that the number of active keys should be less than 10 times your goal throughput per second. So that's similar to the goal sample rate. On the dynamic samplers, we have a goal throughput per second, which is the number of traces you want to let through per second. And basically, you want to make sure that your keys are limited to 10 times that number. Because just like with the dynamic samplers, if you have too many keys, basically you're not going to have enough traffic going through to even hit your goal throughput per second limiter that you're putting in place in the total throughput sampler. So if you set it to say 500 traces per second, but each of your keys is only getting 200 traces per second, you're not going to sample anything because you're under your throughput threshold. So with having all of these samplers available to us in Refinery, implementing them becomes the sort of the art of using Refinery, and we do this through creating rules. So rules are done in a couple of ways. Firstly, Refinery has the ability to categorize traffic based on the environment, the Honeycomb environment that you're sending it to, based on the API keys that are used when sending data to Refinery to Honeycomb. So this is based on your Honeycomb API key. And so you can basically use different samplers within 4 different environments within your Refinery configuration. Now, one of the samplers that we have that's not really a sampler, but allows you to sort of break up your traffic even more, is called the rules-based sampler, which allows you to sort of make more intricate sampling decisions based on the contents of the trace data. So the first part of the rules is breaking things down into environments, which is just done via API key. The second part is that within the environments, you can use the rules-based sampler to make decisions based on the actual contents of your traces. This is where that trace awareness really comes in. So rules are basically defined to process traces based on conditions. So trace attribute has this in it, trace attribute exists, does not exist, things like that. Traces are matched against rules in the order that the rules are written. A rule can have multiple conditions, but these are matched via an AND clause. There is no option right now for an OR clause. When it's matching conditions, when the rules-based sampler is matching a trace against your rules, your rule conditions, it is matching the values of all spans in the trace, not just... So, you could have, if you have a rule that says status code 500 and target is /login, if you happen to have a trace where one span goes to /login, has the target of /login, and then completely different span has the 500 status code, that whole trace will fall under those conditions in the rule. We can improve that. We have a scope declaration where you can say, if I have multiple conditions, all of those conditions need to be true for a single span within a trace. Finally, in our example here, we're just using the deterministic sampler. We're saying sample rate 2, 1, 10. But finally, you can use the dynamic samplers or the throughput sampler within your rules-based sampler as well. So you can use different types of samplers for different types of traffic. Now, everybody's traffic is very sort of individualized to them. The data that you care about is different from company to company. Things are not, people use their data in different ways with different goals in mind. There's really no one set of rules that fits everything, but we do have some sort of starting places that we recommend. First, drop your health checks. If you have, a load balancer or Kubernetes liveness probes or anything like that that's showing up in your trace data, dump it. It's not very useful. It's just taking up space. Finally, we recommend keeping your errors, so having a sample rate of 1 or maybe 2 at the most for your 500 errors or maybe your 400 errors, but also for long duration traces. So like if you have traces that are running 2 seconds long, like that's a long time in the world of web services for the most part. You want to be able to say, I want to keep those so that I can look at that data and figure out where these long duration traces are coming from. We also recommend creating a custom span attribute that can be enabled or with like a feature flag or something in your code, and then you match that span attribute in your rules so that if you add a new service to your microservices, or there's new code, or you've done a major deployment or something, you can basically toggle that feature flag, which will then create the custom span attribute, and then Refinery sees that custom span attribute and says, oh, I don't want to sample those. It's, this stuff is important right now. And then when you're done with whatever that event is, where you didn't want to do any sampling, you toggle that feature flag back off, and Refinery passes over, and then the traces will pass over that specific rule. Finally, for your last rule in a set, for like the last rule in an environment, we really recommend using like a throughput or a deterministic sampler to handle the catch-all traffic. Basically anything that didn't meet specific conditions in your other rules, do something that will be a little bit more aggressive for the rest of the traffic that gets through, because this will sort of eliminate some spikes or some things that you don't expect. It'll sort of force it'll force sort of a more minimal sampling strategy, meaning you're dropping potentially more traffic and saving some more money. If it doesn't fall into a rule, presumably it's not the data that is most interesting to you, so it's okay to have a higher sample rate. We wouldn't set that sample rate to 1,000 or set the throughput goal to 1 trace per second, but you have a deterministic or a throughput sampler sort of as the catch-all, because just leaving it to a dynamic sampler, you will have a whole bunch of stuff that doesn't get sampled because your keys will be all over the place, most likely. All right. So tuning our rules. So once we've gone past the point of creating our initial rule set, and we're working with dynamic samplers and stuff like that, we want to remember that successful sampling works best with larger volumes of data. So back in the beginning of the presentation, sampling 100 traces with a sample rate of 10 was a lot less accurate than sampling 1,000 traces at the same rate. So look at your traces per second, and you want to figure out sampling rules that are going to give you a better picture of you want to figure out sampling rules that are going to end up still being fairly accurate, so that you can base your decisions so that the decisions you make based on that data will be based on good data. So when you're using deterministic samplers, you want fairly consistent volume of traces. You want a higher volume, so that you can calculate out the right sample rate and have a lower standard deviation, lower margin of error, and you'll have better accuracy of the things sampled that way. When you're using dynamic or throughput samplers, keep your key space low, because the number of keys derived breaks up your data. So if there's less data going through a given key, then you're not going to get sampling out of it. Refinery will sample maximally because it's trying to protect you from a high margin of error. Also remember that refinery instances are only aware of the traces that they individually see. So when you expand and you start having a cluster of refinery instances, your traffic is being divided even more. So if one key saw 5,000 traces a second on one refinery instance, and then you have 3 refinery instances, it's going to break that down, and they're going to see 1.3 thousand traces per second. So they're not going to get as high of a sample rate as they would have on one node seeing 5,000 traces per second in that key. So just be aware of that. You can see the effectiveness of your sampling in Honeycomb by running queries against the usage mode. It's a really good way to sort of see put a marker in there when you change your refinery rules, and you can sort of see a difference between the effectiveness of your different rules. Because usage mode shows you only the real data, the real events that you've sent in. Normal mode in Honeycomb takes into account the sample mode, and it does that sort of second part of the process we saw in the beginning, where it divides by the percentage of your sampling rate to show you what the quote-unquote real volume of data is after sampling. So we also have some configuration options in Refinery that will help you tune your rules. So there's a really big one is the add rule reason to trace. This creates a refinery.reason attribute and adds it to your spans, so that you can see what rule a trace went through when Refinery was making that decision, or when Refinery decided to keep that trace. You can see it also will attach, for the dynamic samplers, it also attaches the key to that rule name, so that you can see the different keys that are being created, and you can analyze those and see how big your key space is. Another thing that we recommend, there's a query auth token config value, where you basically create an API key for accessing the query endpoint in your Refinery nodes. This is basically to allow you to validate your configuration and your rules in Refinery. Finally, add span count to root is useful in a couple ways. This looks at the number of spans in a trace, and in the root span of the trace, it will add that count as a metadata. You can use that count in Honeycomb to sort of make assessments of whether or not, sampling those traces is worthwhile. For instance, if I'm sampling a bunch of 5-span traces, then I'm not necessarily going to reduce my event volume nearly as much as reducing sampling traces that tend to have thousands of events. You can also create rules around the meta span count field in your rules-based sampler as well. So that's a nice thing about the add span count to root. So those are some tools that you can use. They're gonna help you sort of hone in your rules so that you're happy with the amount of sampling that you're getting, so the reduction of true events, of actual events, but still making sure that you have the accuracy you need to make your business decisions and your monitoring decisions around the data that's getting to Honeycomb. Just to talk about some references a bit, we have a bunch of documentation on Refinery on the Honeycomb documentation site. There's also more in some of the files in the Refinery repository on GitHub. I really recommend, there's a talk that I mentioned, the talk that Heinrich Hartmann gave at SRECon last year in EMEA. Definitely take a look at that. There's a sampling error calculator as well that he's created, so that you can sort of plug and play with some numbers to calculate that margin of error. We also have a couple of things. So inside the Refinery repo on GitHub, there's a configuration template, there's a rules template as well that sort of gives you example values and more explanations for each individual thing. Each individual knob you can tune. That's really useful. We also have a Refinery starter pack module in Terraform, which will utilize the metrics that Refinery sends in order to provide sort of useful data to see sort of how your rule turning impacts performance, basically, of your Refinery nodes. So those are some useful things out there. But that pretty much wraps everything up. So I want to say thank you all for listening, and feel free to reach out to Honeycomb if you have any questions or want to find out more about Refinery. Thank you.